What I hope to do in these lectures is to tell you something about the science exemplified by this great ruler, and to tell you in this lecture how we came to the stage of being able to make rulers of that kind, and in particular what we mean by measurement, how we measure things, why we measure them, and to talk about the importance of measurement in enabling scientists to do their work and technologists and engineers to build the constructions ranging from the enormous constructions right down to the tiny constructions that are now marvels of exactitude in microcircuits and microelectronics. But the first thing is to discuss the question, which may seem very obvious, as what we mean by measurement. And it is the process of converting our observations of the natural world into numbers, and also our requirements. The value of this in science is that once one has an observation in the form of numbers, then numbers are the raw material of mathematics, and mathematics for our purpose is a kind of logical shorthand, and the application of mathematics and the results achieved by the mathematicians enable us to short-circuit an enormous amount of reasoning with the confidence that whatever comes out will be the absolute rigorous logical result of the numbers that we put in. And the other aspect of numbers is the way in which we can communicate for scientists and engineers and others all over the world the results of observations, partly so that they can reproduce them for confirming our results, and partly because if they want to make something of the same kind, they know exactly how big or small to make it. This is all very simple, and it seems almost too obvious until one begins to think about how do you define what a number is. Now, you will find books on a very important branch of mathematics called the theory of numbers. But when you look there, you won't find a definition of what a number is, because it's one of those quantities or qualities which one cannot put in words in a dictionary such that if you knew nothing about them, you could nevertheless get from the dictionary the sense of what they are. The other aspects I'm going to talk about, like length and time, are in exactly the same category. And in number, we all know what we mean by number until we come to write it out. And to show you the point, let me have a volunteer from the audience. Would you like to come down? And here I have a bag, and how many have I got in it? Can you see?
2.
Right, we'll take those out and we'll put them there. Like that. Now, The bag is now empty, isn't it? Really is empty.
Yes.
Right. So now, let's see if we can work some magic on it. And I wish the bag wasn't empty, you know? But my magic hasn't worked. I wonder if you can do better. Well, now, you put your hand on mine, and you say, you wish. Say, I wish there was something in the bag.
I wish there was something in the bag.
Right, now.
Oh.
Now. Now, will you take them out? And put them down there. There we are. And now, you see, thank you very much. Now, we all know that the number there is different from the number there, 3 as opposed to 2. And because we can count 1, 2, 1, 2, 3, we can say what these numbers are. So from that simple illustration, we have really the basic idea of numbers and the sequence of numbers. But if we're going to write them down and argue about them and argue from them, then we've got to have a form of notation which is comprehensible to other people as well as ourselves. And this is quite a difficult step. The fact is that there's at least one tribe in Africa who cannot count above 3. 1, 2, 3, and after that, the only word they've got is many. And this is exactly the same situation as we were in with radar in 1940, when using the kind of radar stations, the very famous radar stations with their great towers. That's a German photograph of the towers on the cliffs of Dover, taken from across the channel. We couldn't, in those days, we had not got the resolution to be able to see more than 1 or 2 aircraft. After that, we just had to say many. The Germans had to say exactly the same thing. So we were almost counting on this primitive scale of 1, 2, or many. But of course, we couldn't get very far with that. Modern radar, as we'll see later in these lectures, is very, very much more impressive. But nevertheless, it made a tremendous contribution at that time. And the question comes as to how we do indicate larger numbers. Well, various civilizations have had their own systems, and of course one of the most famous, which you can see in many places, is the Roman system. Now, the Romans, they could think of bigger numbers than 3, but the biggest number that they had a symbol for was 1,000. And they had no figure or no way of indicating more than 1,000. And had you been a Roman trying to do a calculation and indicate to other people what it was as 1,000,000, all he could have done would have been to taken his symbol for 1,000, which is M, and write it out 1,000 times. And when you got a system like that, it really becomes very difficult, when you think about it, to do calculations. We have here what the Romans, if they'd been able to do the calculation, would have written for 53 times 26, and if they'd been able to count correctly, and they'd have had to do it very laboriously, they'd have got this expression here. M for 1,000, 3 C's for 300, a 50, 2 20s, a 5, and 3 singles. Whereas we, of course, just do the calculation like that. And what is the great difference? Well, the difference is primarily not the fact that we've got numbers from 1 to 9, all as separate symbols, but this symbol here, 0 or 0. And it's one of the great inventions of the human race. This may never have occurred to you, it didn't occur to me until relatively recently, just how vital an invention this was. Because once you have a sign for 0, then you can do multiplication and division in this relatively simple way, using the placing of whatever figure you've got in the order to indicate units, tens and hundreds and so forth. It was a tremendous step forward, and we in Western Europe owe it to the Arabs, who in the 13th, 14th centuries brought it across. And they probably got it from the Indians, and the Indians probably got it from the Chinese, because there is a symbol for 0 in ancient China. And these are the only civilizations, except for one faraway one, the ancient Maya in Central America, who have ever had a symbol for 0. And it is that realization that nothing was so important that it was worth having a separate symbol for it that enabled modern computation to start. And one of the factors which resulted in the great flowering of science in our Western civilization was the fact that men could now do relatively quickly very complicated calculations. And as one of the outstanding examples, the work that Kepler did on the many observations of the Danish astronomer Tycho Brahe, and he did thousands and thousands of calculations, which he could not have done before without the sign for 0, ultimately enabled him to deduce that the planets moved in ellipses and executed equal areas in equal times, which really provided the clue to gravitation, the challenge to Newton, and hence really the foundation of modern mathematics, modern mechanics rather, and therefore of modern physics, and indeed the basis of all exact science. Now, the 0 sign is vital, as I've said. Are any of the other numbers vital? And the answer is only one of them, and that is 1. And with 0 and 1, you can in fact, using exactly the same idea of using the place in the order of the numbers, 0 and 1, indicate its exact significance. And you know it, of course, as the binary scale, which is the basis of modern computers. And to give you an illustration of how this system works, let us make a binary counter out of human beings. And for that, I want 5 volunteers to come out and stand here. Who are the 5 who are going to come? Well, yeah, you've actually got, we've already arranged this, may I say, to save time, with armbands on, 0s and 1s, so we all face in that direction to start with, and we show our arms as prominently as we can, and you'll see we've got, you stand right in line there, and we've now got everything reading 0, which is indeed exactly the same as the symbol in the decimal scale for 0, which is in the red figures up there. Now, to count, we have just 2 rules, that if you are tapped on the shoulder, you about turn by 180 degrees. So that brings the first tap I give, it gives the first member a chance to turn round like that. And we've now got all 0s except 1, which is just indicates 1 on the decimal scale like that. The other rule we've got to employ is that if you are tapped, whenever you're tapped, you turn round, about turn by 180 degrees. So if I tap you again, you turn round, and every time you find yourself facing the same way, you tap the one in front, who now has the order to turn round like that, And now we have, I've administered 2 taps here, and here we get 1 and 0. 1, 2, 0, so that indicates 2. Now, a tap again, and we've got 1, 1, 3. Now I tap again. Very good. That's right. And now you tap because you've got that. And now we've got, I've put in 4 taps here. The counter has now registered that I've done 4 taps here because there's 0, 0, and 1, 4. Now we tap once again, and now we've got 4, 0, no 2s, and 1, making 5. I tap again, and now we've got a 4 and a 2, making 6, and a tap again, a 4 and a 2 and a 1, no. Only went that way, you faith. Now we've got 7. Now we see something interesting happen. We get a chain reaction, 0, 0. And now we've got 8. We'll just carry on 1 more to show that we get on as the 9 there. So, and now we've got 1, 8, no 2s, no 4s, no 2s, and a 1 here, making 9. So in this way, we have made, as it were, what we could call a biomechanical counter, because it's made of biological structures, but it's working mechanically, and it's giving us an indication straight away which we could read off in binary scale like that. Well, thank you very much for this. Thank you. Now, the importance of this is that this particular system of being able to register just 2 states in each case, and whenever it returns the original state, passing on an impulse, is indeed the basis of the modern computer. And it came about not because anyone was thinking of computing at all. It's one of those cases where an invention which a physicist wanted for something quite different turned out to have enormously important applications. This was Dr. Wynne Williams in the Cavendish Laboratory in Cambridge around 1930, when it was being very laborious to count nuclear particles, but they did actually give impulses when they passed through the counting mechanism. And Dr. Wynne Williams devised what is known as the scale of 2 counter, which worked electronically, doing exactly what we've done just now along the chain of human beings. And that scale of 2 counter was soon seen to have tremendous possibilities. And with the invention of fast electronics, and particularly the invention of the transistor, it became possible to make the most powerful computers working just because of this property of electrical circuits suitably devised to register pulses and count them as we've seen. And in the end, when you think of all the impact that computers have in the modern world, it may turn out to be as important an invention, indeed, as the zero sign itself, or even of the wheel. So we now have available a very powerful system indeed for all kinds of purposes. But now, having got the numbers and got a way of registering numbers for whatever purpose we like, let us look at the other part of the problem. You've got to get what you want into the form of numbers first. And you may need to do this for scientific purposes, but let us take a very simple case indeed of supposing there was a royal institution in New Zealand. Supposing the New Zealanders decided that they would like to have a royal institution, just like this one, and they wanted to build it in exactly the same way. And because this is such a famous lecture bench, used by the great Michael Faraday so very often, this is exactly where he stood and talked. The New Zealanders would like to do that too. And they would ask what the size of the bench was. And supposing I had to give a quick answer, and I had no other method of measuring available, what I would do is what I very often do when I'm caught like this, is to measure the size of the bench by just going heel to toe, 1, 2, 3, 4, 5, 6, 7, 8, and 9, and tell my New Zealand friend, make your bench 9 feet long. But you can see the problem. The problem is, what is the size of his foot? Is it the size of mine? Well, would anyone like to come down? And so we'll see 9 of your feet, you see, and see what size of bench we get. We start from there, that's right. 2, 3, 4, 5, 6, 7, 8, 9, you see. Well, you were 9, 9 was there. So you'll see, if you had to make the bench in New Zealand, I chose 9 feet, it would be rather a small bench. But thank you very much, because this has brought out the point that you need, in order to express something in numbers, a standard which has the same quality of length, and again, length is a thing you can't define in words, but you all know that the thing that separates the property that separates my two hands can be perhaps defined as length, and we've got to have something of exactly the same kind, and indeed, this, or for example that, is of exactly the same kind as the distance between the ends of the bench. And we've got to use that as a standard and say how many times that goes into the length that we're trying to measure. And one must agree on a common standard. And the standard, therefore, has to be something which is reproducible and should be convenient and should also be permanent. And since so many measurements did depend on feet, and indeed we still use the word foot to indicate one of our basic units, have a look at this picture, which comes from a German book on geometry of about 1550. And here you see a group of men lined up, and the only time I've ever seen people lined up like that were not men, but girls in a beauty competition. Well, obviously they are no beauties. So why are they doing it? You see, they're all standing heel to toe along this line. And the purpose of that was indeed to carry out what someone had found, and really it was a very brilliant idea, of getting an average foot, because this was a way in which the average foot in one village could be more nearly to the size of an average foot in another village by having not just picking one man at random in each village, but by taking a number of them. And there was a very precise drill. You waited until church service on a Sunday morning. You stopped the first 16 men coming out. Now, that was a rather dangerous procedure in a way, in that there was an element of selection about it. They might easily be the first 16 anxious to get across the local public house for a drink. But nevertheless, you picked them and you told them to step up and stand along a line. And we will do this not with 16, because it will take rather a lot of time, there isn't much room, but with 8. But can I have 8 volunteers to imitate the gentleman in this picture? And what we do is you all stand as best you can like that, heel to toe, all in a line. You don't have to have both feet, but one foot as there, like that. 1, 2, 3, 4, 5, 6, 7, 8. Yes, we got 8, Bill. So, okay. Now, what the next instruction was, that whoever was the man responsible in the village had to take a piece of string and stretch it out from the heel of the last man to the toe of the first, right? Cut it like that. And now, you see, we've got a piece of string which is equal in length to the sum of 8 feet, in this case 16 feet taken at random. And then to get the average down to one of the 8 or one of the 16, this very beautiful and very simple trick was just to take the string like this, and now that is exactly half, so it's 4 feet. That is now down to 2 feet. And you had to use very flexible string so as not to lose much in the bend. And there is the average foot taken from our 8 volunteers here. A very beautiful trick. Again, you see the scale of 2 coming in. And that was why, specifically, it was 16 men you had to take in order to get an average, which would be on the average the square root of 16, 4 times as less variable than if you'd taken one man alone. Right, so there was the way in which, if you hadn't got a standard, an actual physical standard, you could indeed get a reasonable average. Well, of course, this was a rough and ready method, and when people had to do more accurate things like making guns and so forth, where exact measurements were necessary, one had to have more precise standards, which were ones that you could actually carry from one place to another, or certainly carry copies. And we begin to see the growing importance of a basic system of measurement in Magna Carta. Would anyone like to tell me, first of all, the date of Magna Carta? 1215. And what was Magna Carta?
The document drawn up with King John signed by his barons.
The barons made him sign it.
Yes.
And the clauses which I think every Englishman and every English-speaking person, in fact, it was one of the clauses which the American rebels in 1776 quoted against us, was that no man should be expected to pay what was called scutage, which was taxes, without having some say in the way they were spent. No taxation without representation. That was one of the clauses. Another clause was that there should be a system of laws whereby anybody accused of a crime must be tried by a number of his equals. And one of the clauses, later on, clause number 35, you see, was an indication that the barons realized how important, if you're going to have a civilized structure, a sound national system of measurement was. And so this clause, and we have the replica of Magna Carta actually here. It's a replica like that. And the relevant piece of it we have magnified up on the slide. And the translation runs, "There shall be standard measures of wine, ale, and corn," evidently first things first, "throughout the kingdom. There shall also be a standard width of dyed cloth, russet, and haberjet." Haberjet was another kind of cloth from which we get the word haberdasher. Namely, 2 ells within the selvages. Weights are to be standardized similarly. And so there you see the beginnings of a national system of measurement because of its growing importance. And that is right back in our Constitution in Magna Carta. And it is that fact that suggested to me that an appropriate title for these lectures would be From Magna Carta to Microchip. Now, the next slide will show how we obtained, or tried to obtain, ideas of measurements going back long before that time in our own country, right back to the earliest monuments that we have. And of course, the most famous of them is the one at Stonehenge. Now, that looks perhaps an almost not quite random collection of stones, but when you see it from the air, as on the next slide, you can see it really is a rather precise circle, and indeed surrounded by an equally precise circle. And archaeologists have wondered whether the men who built those monuments, roughly 1900 to 1500 BC, 4,000 years ago nearly, worked to some system of measurement, and whether there was something like a unit, and the length that they found as the most probable length, if indeed there was one at all, was about 5.44 feet. And this figure of 5 feet, particularly, keeps on coming up because we talk about miles still, and we get our word mile from the Roman mile. The Romans called a mile milia passium, which meant 1,000 paces. And the Romans counted their pace as the pace not between one leg and the other, but between the same leg coming down again. So in a way, it's what we call a double pace. And you'll see 5 feet multiplied by 1,000 is 5,000 feet, which is very near our mile of 5,280. So, the pace of the Roman army, the step, was indeed 30 inches. And that pace has survived to the present day because it was also the pace of the British Army, and it is the pace to which most of our regiments, and the most famous of all, those in the Brigade of Guards, are trained. And the occasion on which we see this most dramatically, of course, is the trooping the colour. And we're going to run a very short spell of a rehearsal of the trooping, which has been recorded. But before we do, let me just show you this picture of guardsmen from the 5 regiments of the brigade, because again, if you can count, there's a coding which will enable you at once to tell to which of the regiments the guardsman belongs. Here on the left is the grenadier, the senior regiment, first in the order, and so he has his buttons in ones. The next senior regiment, although they would say they were the first, is, because their motto is nulli secundus, is the Coldstream, and they indicate, nevertheless, their position in the brigade by their buttons, which are in 2s. So we have the right of the line, the grenadiers, left of the line, Coldstream, buttons in 2s. The third of these famous regiments, the Scots Guards, number 3, have their buttons in 3s. The Irish Guards have their buttons in 4s, and the Welsh Guards, the newest of the Guards, have their buttons in 5s. And if you can count, and you know that coding, you can tell at once which regiment is involved. So now let us look at this very short excerpt from a rehearsal of the trooping, which will show some of the precision which is achieved. Now, if you're quick, I think you can see that those buttons are in 3s, and the tunes would also tell you it's the Scots Guards. That also shows you it's the Scots Guards too. Now, I thought you would like to see something of the training that goes into the achievement of that precision. And the commanding officer of the Irish Guards has very kindly allowed Company Sergeant Major Brown of the Irish Guards to come and show us how it is that he trains guardsmen to march with the standard pace of 30 inches using a device that looks like a compass, which is called a pace stick. Company Sergeant Major Brown, Irish Guards. And the Sergeant Major will first show us how he does it in this very, very limited space. It's a tremendous feat, I can assure you, to be able to do it in such a limited space, how he uses the pace stick to train in slow time and then in quick time.
Slow march!
And so, Sergeant Major, we are most grateful to you and the regiment for being with us. If we can have the next slide, which I think will show how the transfer was gradually made from these very human measurements like feet and so forth to precise standards of fair permanence. And we go from the yard bar of Henry VII to the new bar of the reign of Elizabeth and to the imperial standard yard, which you can find an example of in Trafalgar Square. And then there's an interloper in all this, the International Prototype Meter. And although the yards, feet and inches served the purposes of certainly the British Empire very well for a very long time, when the French Revolution occurred, the scientists associated with the revolution had some fundamental ideas. And there was a difficulty with ordinary standards. They do change their size. Metal, over the years, may well shrink. The standard yard, the bronze yard there, for example, has shrunk by about 2 parts in 10 million between about 1897 and 1945, because the atoms in the metal were rearranging their positions. And it would be good if one had an even more permanent standard than a bar of metal. And it would also be a very good thing if it was something which, even if a calamity happened and there'd been a fire and the metal had melted, nevertheless, measurements made after that could be related to measurements made before that catastrophe. And so the idea was to have some sort of eternal standard which could be used. And what the French scientists argued with impeccable logic was that if one could use some dimension associated with the Earth, this would be ample. Because if something happened to change the shape or size of the Earth, it must be such a catastrophe that there'd be no human beings left afterwards to measure anyway. And so they took advantage, they thought, of the fact that the Earth was known to be approximately a sphere. And despite all the people who argued the Earth was flat, it had been known from about the year 230 BC that the Earth was approximately spherical. And it was due to the librarian of the University of Alexandria in those days, Eratosthenes, who had noticed one very interesting fact. He, you see, lived somewhere about here, and you can also see it on the slide if you wish. And when he stuck a vertical stick into the earth at the Alexandria, of course, the sun cast a shadow. And that shadow, through the year, got shorter and shorter until on the 21st of June, at noon, the shadow was at its shortest, and it subtended an angle at the top here of 7 degrees, 12 minutes. Now, that was interesting, but not significant until Eratosthenes also knew that if you did exactly the same thing at a point, Syene, which is up the River Nile, and is, I should have said he was there, and somewhere about here, if you stuck a similar stick in the ground vertically, the shadow also grew shorter, but it grew so short on the 21st of June that there was no shadow at all. The sun was absolutely overhead. And Eratosthenes argued this must be due to the fact that the earth was curved like that, and there was this angle between the vertical at Alexandria and the vertical at Syene. Now, 7 degrees 12 minutes, if you multiply it by 50, comes to very nearly 360, in other words, a complete rotation. And so what he'd chosen, by good fortune, perhaps, was roughly 1/50th of the Earth's circumference. And so if you knew that distance, which he did, it was roughly, in our terms, 500 miles, and you multiplied it up by 50, you'd get the whole distance round the Earth. In other words, 50 times 500, 2,500 miles. So 25,000 miles, sorry. And so really, from those days, the fact that the Earth was curved and that it was reasonably spherical and the circumference was about 25,000 miles was in fact available knowledge. And so what the French scientists said they would do would be to take the distance. They thought they might take the distance from the pole down to the equator or through one pole to the other. But in the end, of course, they couldn't get at that, but they decided they would take the distance from the pole round to the equator, like that. Well, when they did that, they said, well, it is too big. It's about 10 million times too big. So we'll divide it by 10 million to make it something like the size of a yard. And so when they divided it by 10 million, it came down to 39.37 inches. They said that we will call our standard, we will call it the meter. But it's related to this distance. Now, it wasn't very long before they found that they had not measured this distance accurately. They couldn't, you see. The state of surveying, geodesy as it's called, was not really great enough, and they hadn't got a very big arc, and it was a very difficult thing to do anyway. And then they were faced with the problem. Do we define the meter as 1/10 millionth of the distance between the pole and the equator, and do we change it every time we measure this distance more accurately? And that meant every scientific measurement would have to be recalculated every time someone made a remeasurement of this. And in the end, they gave it up. And they said, it's no good. We'll have to go back to the bar. But they went back to the meter bar rather than the standard yard. And so really they were almost back where they started. The idea was a good one in some ways, logical but impractical. And the only real reason why the meter became so powerful, so much so that we ourselves have been metricated for the last 10, 15, 20 years, is because of one other factor, that they divided the meter up into centimeters, 100th, or millimeters, 1,000th, or nanometers, 1,000 millionth, and so forth, or multiplied it up by 1,000, making a kilometer, and so forth. And the fact that these measurements were now expressed in powers of 10, and this was before the use of the binary scale, of course, in computers, meant that it was much more convenient than yards, feet, and inches. Although, as we can see now, the British idea of the inch splitting up into halves, quarters, 8, 16ths, 32nds, and 65ths really would have fitted in very well with the binary scale that now we have to use so much in computers. But anyway, the meter won out, not because it was a good logical unit, but because of the system of powers of 10 which were associated with it. So we now get to the stage where we have universal measurements which can be reproduced in all parts of the world based on the meter. And for all intents and purposes, that is good enough for us now. Perhaps one of the most outstanding achievements of that technology was the link-up of the Apollo, the American Apollo, and the Russian Soyuz spacecraft about 140 miles above the Earth in 1975. Now, those two spacecraft had been launched in quite different countries by men who'd never met one another. They were traveling at speeds around 18,000 miles an hour. They had to be approaching one another and control certainly within 1 mile an hour. They had to be at the right height. Everything had to be right. And when finally they came together and docked, the part made in America had to fit into the part made in Russia, just like that, so that no air would be lost to the outside empty space, and the two sets of astronauts could walk from the one spacecraft into the other. Now, when you think of the achievement in sheer measurement of some engineers in Russia and others in America who probably never met one another, but because they could agree on a common standard, in other words, the meter, and because they had means of reproducing the numbers on either side to this degree of exactitude, this fantastic technical feat became possible. And that is an example of the enormous part precise measurement plays on the international scale, and of course in ordinary industrial society such as we live in, with the fact that it is so much more economical for factories to specialize. It means that motor cars can be made where you make the back axles, for example, in one factory, the gearboxes in another, the engine somewhere else, and when you bring them all together on the assembly line, they fit. And this is because each factory has been able to make the vital dimensions within the necessary degree of exactitude so that they all marry up like that. And it is that which has made mass production in distributed factories possible, which has resulted in the development of modern industrial society, with all its achievements and, of course, with all its problems too. Because men having to do two specialized jobs can so easily get bored. It's a soulless thing when they only see parts of the construction, and one gets all kinds of human problems arising, again, out of our ability to measure. Well, for the rest of this lecture, I would like to give you, how have we got? We've got about 5 minutes more. I'd like to talk about one or two of the techniques of measurement, which are very simple, but which nevertheless are lessons which are worth learning. And I think the one that I will concentrate on now is the difficulty of making a measurement. And very often one wants to make a very small measurement. A lot of this work is rather like a detection novel. That is the small clues, quite often you've got to look for, in the presence of a lot of big ones. And it's the small clue that gives the game away. And one of them is, for example, supposing we wanted to weigh ether vapor. I've got some ether. Ether is well known, of course, as an anesthetic, and it becomes this is a very important thing that one can show so very easily. Now, if I were to take that beaker and pour some ether vapor in and put it onto a spring balance in the ordinary way, you wouldn't notice the difference. The increase in weight of the beaker with ether in it would be so small it wouldn't notice. But if you make a comparative measurement, the difference can be shown up. And here we have a comparative measurement between a beaker here and a beaker there, and if all is well, the two will balance reasonably. In fact, this one is perhaps slightly heavier. Well, let us see if we can put some ether vapor into the one balance, and because ether vapor bends the light going through it to some extent, you will find it bends the light from the lamp there, and, well, if I hold it out here, for example, do you see it's heavier than air, and therefore there's no liquid coming out, it's just sinking. Now, if I can tease the vapor into the thing here like that, it's tending because of the draft to go out, but we'll see if we can trap some in the beaker, and you'll see slowly the pan, if we can coax it in, there we go, and you'll see the beaker. We're now measuring the ether vapor weight. If we can keep it in now, goes down like that. And we can try to restore the balance by putting some ether vapor into the other beaker, like this. It's a case of judging the draft and where it's blowing. Let's see if we can pour some in here. You can see, I hope, that there's no liquid ether going in, but some of the ether vapor, when the draft isn't too bad, is actually going in, and we can make the balance again. In fact, probably weigh it down a bit on this side with luck, like that. And let us empty both the beakers now of ether vapor. You see, there's the beaker, and you see the ether vapor come out, and we'll take this one, turn it up, and out it came. So there is a way in which you can detect a very small change very easily, all by sheer comparison. And the other thing I would like to show you is one which is connected with the Royal Institution, and it's the problem of measuring a small change in electrical resistance. It is by a device called a Wheatstone bridge, because it was popularized by Sir Charles Wheatstone, who many times had demonstrations here, although he usually didn't give them himself. Faraday gave them instead. And it is properly called Christie's bridge. And if you had an electrical resistance and it was changed very slightly, this was a very sensitive method of detecting the change. 4 resistances, and if you arrange the ratio of this to this, the same as that to that, no current flows through the galvanometer. But if one changes very slightly, then it disturbs the balance and some current flows through. And it's quite easy, as a result, to see changes in resistance. And here we have 2 resistances. Got one. Well, we'll put one on for the moment, and if we can, so is it this one? And you'll see well, it doesn't make any difference, my holding it at all. The resistance is not changing perceptibly because it is not changing very perceptibly the current flowing through it. But if we use two resistances exactly as similar in the bridge, and we balance the bridge to get zero current, or somewhere, look on, now if I see at once, and if two volunteers would like to come up, all right, you two come, and we can have a competition to see who's got the hottest hands. Now, no, don't cheat. You hold one, you hold the other. Oh, someone's... Yes, who's pulling it that way? Will you take a hand away? Yes, I think, well, you've got the bigger hand anyway, slightly. Well, thank you. You'll see how very sensitive that method is. Now, this would be an appropriate point. Thank you very much. There, a change of a few parts in a million of resistance was very easily being detected. And this bridge technique is very important throughout the whole of electronics. Now, Sir Charles Wheatstone figures largely in the history of the Royal Institution because he was due to give a lecture here in 1846. And at the grand moment when, what he'd have done with television, I don't know, but what in fact he did here, he was so nervous that instead of appearing outside the door, he ran away. And Michael Faraday, who was resident here, had to step into the breach and give a discourse instead. And Faraday said he would never have given that discourse if he hadn't quite suddenly been taken unawares and had to do it. And so he did. And he gave utterance, he said, to thoughts which he'd had for some time, but he didn't think really were appropriate to reveal to the world. And these were his thoughts on what he called ray vibrations, that these magnetic phenomena that he was exploring might be propagated as vibrations along lines of force. And years later, that lecture, which was published, was read by a young man, James Clerk Maxwell, and it was Faraday's thoughts on ray vibrations that prompted him to formulate the famous electromagnetic theory that light itself was an electromagnetic wave, propagated according to electromagnetic laws, from which he predicted there could be other electromagnetic waves, which led to Heinrich Hertz discovering radio waves, with all that that has meant for us. And really it all came out of Wheatstone running away. And I think Faraday knew Wheatstone was likely to do it because some years before, Wheatstone had been due to give a lecture here on musical instruments. And although he didn't invent the bridge, but popularized it, the Oxford Dictionary of Music says he invented another instrument, the mouth organ. But again, probably the first time the mouth organ was demonstrated in England was here on the 21st of May, 1830, again by Faraday, because although Wheatstone had done a good deal to invent things like the mouth organ, nevertheless, he was so nervous that he couldn't do it himself. And so I think it might be an appropriate point to finish with. No microphone? It'll come on here. Okay. Well, and it seems appropriate that since, indeed, it would have been most appropriate in that trooping rehearsal if we had seen the Irish Guards and heard their regimental march instead of the Scots Guards' regimental march, in tribute to the Sergeant Major and his regiment, if I can do one of their regimental marches for him.